Lesson 8.1b is going to kind of extend this concept of how A impacts our graph, our parabola, but it's going to be different. You're going to have a parentheses around this. A is going to be inside of that parentheses, and that's not really going to change what the graph does very much, but it is going to change how we interpret it, how we look or describe what is happening to the graph. Okay, so the big thing here is if you thought, oh, look, this time she put parentheses around it, she must have just, made a mistake or something. That's not true. These are actually a very important distinction between this lesson and the previous lesson, 8.1a, where there was no parentheses. So that's not just an arbitrary, like, oh, sometimes you put it, sometimes you don't. It actually makes a very big difference. Again, not so much in what the graph does, but how we describe what is happening to the graph. So in lesson 8.1a, where there was no parentheses, that meant, and you saw this in your practice, that we were squaring first, and then whatever that output was, then we multiplied it by the value of A. So multiplying by A happened after we took our input and we squared it. And because it happened afterwards, because of order of operations, we described those changes from a vertical point of view. So when we did this, when we started talking about this, we talked about the changes happening from a vertical perspective, whether that be vertical shrink or compression or a vertical stretch. And so we looked at it happening like this along the y-axis because it was happening to our output. It was happening to the output of x squared. So it wasn't until after we squared it and then we multiplied those values or those changes that A was creating was happening to our output. So we looked at it from the y-axis perspective, which is the vertical perspective, because it happened to our output. Remember, the y-axis is always the output of the function. So today, what I want you to notice is that A is being multiplied with x before the squaring happens. Okay, so we consider this as changing the input, okay, changing the x value before the function itself squares it, okay? And so, again, the graph is going to do very similar things. What's going to be different is our interpretation or our description, okay? So, how do we graph quadratics in this form? We're going to graph them like we did before, but when that A value is between 0 and 1, we're still going to get a wider graph, okay? This is still going to look wider, okay? This still looks wider. But we are now going to essentially take off our vertical goggles. I think of them, I don't know why. I think of them as goggles, right? I'm going to take off those vertical goggles that we were wearing yesterday, and I'm going to grab my horizontal goggles. And I'm going to describe this as how it is happening horizontally or along the x-axis. So when that A value is between 0 and 1, we're still going to get a wider graph. You can see that here. But now we're going to describe that graph from a horizontal perspective. And a wider graph from a horizontal perspective is like taking it and stretching it horizontally, stretching it from side to side. Kind of like my little rubber band experiment that I showed you in class. If I have this and it gets wider, it's like if I grabbed it from the sides and I stretched it horizontally this way, it would get wider, right? So it's still going to look wider, but now we're going to describe that as a horizontal stretch. The only difference is the parentheses is basically implying that our input is being multiplied or affected by that coefficient before it gets squared. So the change is happening along the input or the x-axis instead of along the y-axis like yesterday. So with it on the inside, when A is between 0 and 1, then it is a horizontal stretch, and that horizontal stretch is still going to look wider. We're just describing it from the side-to-side perspective, okay? If A is greater than 1, if it's a large number, okay, then it is still going to get narrower. It's going to get, but if I think of it, how would I make this get narrower from a horizontal perspective, that would be a horizontal compressing, right? It would be us coming and squeezing in, and it would get long, you know, and more vertical looking, but it would be from that horizontal perspective. So when A is greater than 1, then we're looking, and again, and it's on the inside, then we're looking at a horizontal shrink or compression. And it's going to look narrower. Okay, but we're describing it differently. So the larger A value will always make it narrower, whether you did it like yesterday or today. It's how we describe it. It's whether we look at it from a vertical perspective or from a horizontal. If the A is on the inside of the parentheses, then we're going to interpret or look at that from a horizontal point of view. And so from a horizontal point of view, a narrow graph is like a horizontal compressing or shrinking. And from the sides, it makes it look narrower like that, okay? And then the stretch is the wider one where we stretch it out. And that's really the only difference, okay? Now, the other, well, that's not the only difference. There's one other big difference I was about to say. This is big, so highlight it, do what you need to, because this is the other place that's a little funky, but it's still true, and we still have to know it, okay? In addition to kind of using our horizontal goggles and describing these from a horizontal perspective, in addition to that, the scale factor that we describe is actually going to be the reciprocal of what we typically would say, okay? So in other words, if my multiplier was 2, but it's on the inside, right? And then when I go to describe, let's say it's a 2, so it's on the inside. So I would say that's a horizontal compression by a factor of. Before I decide the factor, I'm going to take the reciprocal of that, and I would say by 1/2, because 1/2 is a reciprocal of 2. Okay, so let's just take a look at that in action. Okay, let's take a look at number 1, for example. We want to graph the function, and then we want to compare the graph to the parent. Okay, so I can see that this is positive on the outside. By the way, if I have a negative on the inside like this one, once I square it, that's going to cancel out anyway. So I don't have to worry about negatives on the inside because the squaring is going to always turn them positive, but I do need to worry about the ones on the outside. Okay, so on the outside, this is positive. That means I expect an upward opening parabola. And so I'm going to just focus this on the top quadrant here. And these guys still are just that simple ax squared, whether it's parentheses or not. That means my vertex is going to stay put right there at the origin. So I'm going to center this as well. Okay. And maybe, since I know that this is going to grow pretty fast, maybe I'll go up by 5. So this might be 5, 10, 15, 20, 25, 30, 35, and 40. This would be 50 up here. Okay, and I'll just keep these by 1s. Okay, so 1, 2, 3, 4, 5, -1, -2, 3, -4, and -5. Okay, we'll have one nice graph right in there. All right, and then let's go ahead and put the parent in there so we have that point of comparison. So we already know the parent is just at 1, 1, which is probably going to be about right there. 2, 4, which is probably about right there. 3, 9, which would be there. 4, 16. So this would be our parent. I know it looks kind of wide, but that's because my scale here is very big. But those would be the points on our parent function. And then I'll just copy them to the other side. So our parent is going to look something like this. So we'll call that f of x. So we know that's the parent. Okay. Now let's compare how that looks compared to this guy. Okay. And you're welcome to use a calculator. But the big thing is we would multiply our input first and then square it. So if I start at 0, 0 times 5 is still 0. 0 squared is 0, so we're good there. But then when I plug in a 1, I'm going to do 1 times 5 first and then square that. So I'll be all the way to 25 right away. And I'll just copy it over. And for 2, for example, 2 times 5 is 10. 10 squared is already at 100, right? So that's already like super big. So our graph, of course, as expected, with that a value of 5, grows very quickly and looks very narrow. Now, that's fine, and that's great. This is our new g of x. But let's talk about the description, because that's what I really want to focus on, okay? So, for the description, we're not going to talk about this from a vertical point of view. We're now going to talk about it from a horizontal point of view. If it's on the inside of the parentheses, we're going to describe this narrow graph from a horizontal perspective. And since that a value is greater than 1, it's going to be a horizontal compression by the factor of 1/5, which is the reciprocal here. So I would say here that g of x is a horizontal compression by a factor of, and then it would be the reciprocal of that a value. So in this case, it would be 1/5. And there was nothing else happening, right? It didn't get reflected, nothing else. That would be my only description that I would be required to do. Okay? Number 2, I'm not going to graph it just for sake of time, because I promised you guys a short video, but I do want y'all to notice 2 things. First of all, if there's a negative on the inside, when it gets squared, that's gonna go away. And in fact, you can look at it here. So I don't have to worry about a negative on the inside. If I put my negative inside of this parentheses and then I square it, you're going to notice our outputs. Oh, sorry, that's mine. Well, there you go. It's still upward, right? It's still upward. You can see my outputs are still positive. So that does not cause a reflection downward, because it's on the inside. That negative gets cleared when it gets squared. Okay, I don't have to worry about the negative. The 4 itself is greater than 1. So if I had graphed this, I would expect a horizontal compression. So I could say that here. I would say m of x is a horizontal compression or shrink by a factor of, and then it would be the reciprocal of that 4, which is 1/4. You don't have to worry. Remember, it's the absolute value. It's the absolute value. So we drop the negative. We're not worried about the sign. The sign is not going to have any effect. Your compression or shrink factor should always be a positive number. So keep that in. Okay. And then if you graphed it, and again, I graphed it here, you can see, sure enough, it is positive, very narrow. If I compare that to the parent here, you can see it's a lot, sorry, oh my gosh. It's a lot narrower than the parent. Here's our parent, there's a new one. But I would be interpreting this from a horizontal point of view. So I would consider that a horizontal compressing, pressing into it, kind of grabbing it from the sides and pushing in. And that's how you would get that steeper, more narrow looking graph. But then the other thing is take that absolute value of A and use the reciprocal as your compression factor. Okay? So in other words, compressions should always have a smaller factor. All right, let's try number 3. I think this one's pretty interesting because it does have like signs and stuff and all kinds of things going on here. So let's try this one. We'll do. First of all, we don't have to worry about this sign inside. That's not going to reflect it across the x-axis. No worries here. But this will reflect. It's on the outside. It's happening after we square. So this will cause a reflection. Okay, I do have to keep in mind and describe that. Okay. Then let's talk about what that 1/5 is going to do. That 1/5 is between 0 and 1. It's a smaller number. So we are expecting a wider looking graph, and we're going to describe it as a horizontal stretch. Okay, so that's what we're expecting to have happen, but let's go ahead and graph it. Since it does reflect, I'm going to have values both on top and bottom. So I am going to go ahead and put my x-axis a little bit more centered. Oh, what happened here? My pen stopped working. Of course. Let's try that again. Sorry. So there's my x-axis, here is my y-axis. Probably just going to go with a more standard graph for the parent here. So we know our parent is just at the origin, and then 1, 1, and then 2, 4. So this would be our parent right here. I'm just going to go by ones. I promise you're going to get to be such a pro at graphing this parent function. You're going to be able to do it in your sleep. So there's our original parent. Let's talk about how this one is different. And you can definitely grab your calculator to do that. So for this one, we have a negative on the outside, parentheses, and then negative 1/5 x. Close that parentheses, and that gets squared. So make sure you're entering it the correct way, and then we should be able to pull up a table of values. Okay, so according to this, again, we expected it to be at the origin, and sure enough, our table concludes that it is at the origin, the vertex. And then at 1, we are at negative 0.04. Wow, that's small. Very close to the x-axis. At 2, we are at 0.16, still super small. Okay. At 3, we're about negative 0.36, so about a third of the way there. At 4, let's see, 4, we're just about past the halfway mark at 0.64. At 5, we are at negative 1. Wow, pretty wide, right? And then we just copy it to the other side. So this is all just so tiny, it's almost imperceptible to the naked eye. But here's our graph. As expected, very wide with that 1/5. There you go. So very, very wide. Cha-cha. There we go. This is our R of X graph. Very wide because of that. And then, of course, flipped downward because of the negative. Okay. So I want to describe both of those things. We're going to say this is R of X is a reflection across the X. Okay, but it is also a horizontal, so we'll say and a horizontal stretch, right? So from a horizontal perspective, that wide graph, it's like if we had grabbed the purple one and stretched it out. So horizontal stretch by a factor of, and again, we're going to take the reciprocal of this. So if I flip that fraction, it's just 5/1 or just 5. So a stretch should always be a large number, okay, or greater than 1. Okay, so there's that example there, very, very wide, but we're looking at that from a horizontal perspective. Okay, so that's really the only difference. When you're looking at that on the inside, the graph itself is going to do what you expect it to do, but the way that we describe it is going to be from that horizontal perspective, and your factor, stretch or compression factor, will always be the reciprocal of what you had before. Okay, so flip it over. We'll finish out with a couple of word problems here. They're actually a little bit easier, I think, than what we just did a moment ago, because you have a nice little picture already drawn. Let's look at number 5. So it says the diagram shows the cross section of the satellite dish. So cross section, kind of like if you cut it in half, where x and y are measured in meters. Find the domain of the width of the range. Find the domain of the width and the range of the depth of the dish. So we're looking across this way, how far does it go, and this way, how far does it go? So it's not too bad, as long as you know that for the domain, we're looking at on the x-axis, what are the widest x coordinates that we have values for, right? Well, how far out does it go? That's what we really want to know. So based on this picture, it looks like the satellite ends at an x coordinate of -2. And then it goes, and then the other end of it is at +2. So at -2 and +2, that is where the furthest, widest, most points are on that x-axis. So then we can conclude that our domain is the set of x's between -2 and +2. That points for everything in between. And then we'll do something very similar for the range, which is this way, vertical. What is the lowest y coordinate that we have a point on our satellite for? And what is the highest y coordinate that we have points on our satellite? And according to this graph, the vertex of this is at the origin. And it looks like all of these points on this curve go all the way to that -2 and that +2, both of which are lined up with a y coordinate of 1. So it looks like it goes all the way up to 1 and then nothing past that. So here we would say the range would be all of the y values between 0 and 1. So it's everything from here to here. We have x values for everything in between. And then from here to here, we have everything. We have y values in between. Okay? Not too bad. Let's take a look at number 6. The diagram shows the cross-section of a soup bowl where x and y are measured in inches, and find the width and depth of the bowl. So same concept, right? We want to know what is the widest part of the bowl and how far does it go on the x-axis, and it looks like it goes to -4 all the way to +4 and nothing further. So we would say here that our domain is everything from -4 to +4 on the x-axis. And then for the range, we'll do the same vertically. What is the lowest and what is the highest? That's what we're looking for, right? So looks like our origin, once again at the vertex and the lowest point, and then it goes up all the way to this part right here. I marked it there, but that's really the edge of the bowl. The furthest x value is really paired up with y = 2. So that is really as high up it goes. It looks like it goes higher because they're making it three-dimensional, but really it's here. That's the edge of the bowl right there. Okay, so for the range, it would be all the y's between 0 and 2. That would be your range. Okay, like I said, those are a little bit easier, being able to determine the domain and range there. Let's finish it out with a couple of those always, sometimes, never. Those are good thinking problems. So determine whether the statement is always, sometimes, or never true, and make sure you are ready to explain your thinking here. Okay, so it tells you here the graph of f of x, looking like this. This is the new one. Notice a is on the inside, opens in the same direction as the graph of g of x equals dx squared, where a squared is equal to d. Okay, so what I like to do is first I like to rewrite this one by substituting this in. So what they're really telling me here is that g of x is equal to, and then instead of writing d of x here, or d, I'll write a squared. That's what I meant to say. So d is a squared. Since they're equal, I'm substituting it in right here. Okay. But we know that this right here is the same as a times x squared, right? Because if I distribute that x, that power I mean, it's the same as that. So those two things are equivalent. And that's what f of x is. This right here is what f of x is. If I take that f of x and I distribute my power, I would indeed get the same thing. Okay, so would these guys open the same direction? Yes, always. They end up really being the same function. Okay, so especially since we are squaring them, both g of x and f of x, both of these guys will both be positive. And they will both open upward. Open upward. Okay? All right, let's try number 7. The graph of f of x equals, again, ax in parentheses squared. And they're telling us that that's going to be narrower than g of x, which is dx squared, if d is less than a squared but still positive. Okay, so they're telling us it's positive but it's less than a squared. Okay, so again, if we distribute here, we know that just to compare these, if I distribute my power, I know that f of x is really that. And if I substitute this in, what they're telling me over here is that g of x is going to have an a squared, or a value that is greater than that a squared. So here, this d of x is going to be a greater value, which means that this is going to be narrower than this guy. And this one would be wider. Since d is greater than a squared, or you can think of a squared as being smaller than d squared, that is going to be wider than that. And so, will this one be narrower than that one? Never. Okay, a smaller a squared value will result in a wider graph. Okay, so it's understanding those relationships between the larger the number, the narrower the graph, but also being able to interpret it from a horizontal perspective. So whenever you see those parentheses, that means you're going to have your horizontal goggles and you're going to describe the same things we saw last time, but from a horizontal point of view.